So let's take a close look at the general framework of the machine learning, right? Let's using image recognition as example, right? So you have an input image, then you want to find a mapping function, right? Learn from the machine learning algorithm and to give out like a prediction, right? It's cat or dog or whatever. So typically, we can think of a lot of functions, right? So basically, a function, you have a couple of a couple of parameters, right? So you can change the parameters, then it will change the function will give you different output, right? So maybe, let's say I have a couple of functions here, right? F1 is one function. And, if you use that, it will give you output this image as a cat, this image as a dog, right? If I take another function, F2 here, it will also give you output, but it's going to be a different set of output, possibly, right? Here, give you, this is a money, and this is snake. So we can consider this function going to be learned by the model, right? So you have a set of functions. And in this case, we want to, train the model so that it will give us the desired output, right? The correct output. So what we do is we're going to leverage something, right? Particular the training data, right? To train this model to give us the desired output, right? So for this training data, you basically have the input image, right? Because we are doing image recognition, right? So for the training data, we have a set of training images. And you also have the corresponding labels, right? We consider this is a ground truth, right? Maybe this is annotated by a human, right? So these are absolutely right. So this is the label for this image, and this is the label for this image, right? So on and so forth, right? So you have a set of training data, okay? And so basically we're using this training data and train this, the model, right? Because in the very beginning, you can, have, all sorts of parameters and give you a set of functions. But we want to using this training data to guide the training process and give you a model that is able to predict the desired output. So we want to, have an evaluation, right? How good is the function? So if you look at these two examples, right? If we, using the classification accuracy as a measure of how good this function is, right? Let's just take a very simple case here. We only have two training data, right? So one image is cat, one image is dog, right? So in this case, we can compute the classification accuracy. This is 100%, and compared to this function, F2, and this is basically 0%, right? So obviously, this is a better function, and we want to use that. So because we have this training data and the corresponding label, right? So this is called supervised learning, right? Because we are giving this label data, right? This is the human supervision. These labels are generated by human annotators, right? So we give this kind of knowledge and to train the model, right? So in a supervised way. And once we use this kind of some sort of metric to evaluate the function, right? For example, the classification accuracy, then we can, pick the best function, right? And then we can using this like the best function to do the testing or the inference stage, right? So which means I can, give you a random image, which is not, belong to the training data, right? Then the model will also give me a very accurate prediction, right? So this is another cat, right? Not necessarily the same cat image in the training data, but have the same semantic label. But this model is able to, predict this image correctly as a cat class. So this process is in general called training, right? So you have a data set and you train the model and have some measure to evaluate how good is the model is, and finally you pick the best function, and then you just take that model or function to do the testing for some of the new data. So yeah, so this basically summarize, these, 3 steps. And next, let's, go through each of these steps, right? So first is define a set of function. Okay. For here, we specifically consider neural networks, right? Because we are studying deep learning. So here is, basically the structure of the neural networks, right? So it's a simple function, and we'll take some of the input. So here is an input vector, right? A1 to AK here. And each of these will connect with a weights, okay? So W1 to WK here. So these are the weights, and you can do the summation, and then we'll add a bias term. Okay, so you take the summation and we add a bias, you generate output Z, right? So you can write, the equation as follows, right? And also we'll have an activation function usually. So here we have the activation function sigma Z here. And typically, we'll specify some of the common activation functions, but here just give you like a numerical demo, right? So what this neuron will do, right? So here, let's specify this is the bias, okay? And these are the weights. So I'm just making some numbers up, okay? Not necessarily this is the actual weights in the neural network, but just initialize in this way. So these are the weights. And maybe this is the input, right? So based on the previous slides, right, we do this kind of multiplication and we sum them up. So we have, 2 plus 2 minus 1, and we will also have to add in the bias, right? So we end up with a value of 4, and then we go through this activation function, okay? So there's different types of activation function, but here we'll just look at the common activation function called the sigmoid function. Okay, so this is the plot of the sigmoid function. So basically, we'll squeeze any number, into a value between 0 and 1. Okay, so that's the output. If you have a 4 going through this sigmoid activity function, this is the output you'll get. Okay. So once we're clear about like the basic structure or a working mechanism of the neuron, and we can stack or piece combine different neurons together to form a network, right? So maybe we can put them in series, right? So we can also put them in parallel and also combine different neurons, right? So we can have different connections essentially, and this will lead to different network structures, right? I can change this, I can add more here, right? I can change the connections, right? And this will lead to different network architectures. And the neurons will have different values and weights and biases, right? You don't have to necessarily have the same set of weights for this neuron and this neuron and this neuron. You can specify different weights and the biases, terms for different neurons, right? So, and these can be learnable, okay? So, in this case, the weights and the biases are considered the network parameters, right? So we can using theta to kind of capture, right, or kind of to indicate this is the parameter of the particular network, right? So that consists of all these weights and bias terms of these neurons. Okay. So let's look at this very simple network. This is called fully connected feed-forward network. Okay, so the fully connected means, right, so these are the input neurons, and these are the hidden, we call this hidden neurons, right? So each neuron is going to have a connection with all the neurons in the previous layer, right? So these called the fully connected. And this is basically very simple, right? You only have a couple of layers, and each of the layer you have like 2 neurons. And let's still make up some numbers, right? Let's say this is the weights and this is the bias. and we have this input value, right, for these two input, 1 and -1, and we can easily compute, right, with this element-wise multiplication, and this is 4. If we specify, we're gonna using the sigmoid function, for the active function, and we can get a value, right? So we can, do this for this neuron, right? We can get this output, okay? So then for the next layer, right, next layer of neurons, so this output of the previous layer of the neuron we'll consider as input, right? And again, we'll go through this multiplication with the weights, for this neuron and the bias term, and basically the same operation, right? If we specify a different set of weights and a bias, right, for these two neurons, and we can repeat the process and we can compute the output, right? So we can do this for the next layer, and eventually we can get these two outputs. Okay, so if we get a different input, right? So before this is input 1 -1, right? We have input vector 1 and -1. And if we change to a different input vector, the weights will be the same, and we get a different output, right? So basically this network architecture, right, and the weights and the bias terms, and specify a specific mapping function, right? If we change these weights, we'll change to a different function. So this network can actually define a set of function, right? This is going to be determined by different weights. So we also have this input vector and output vector, right? So we can simply write this, in a vector form, right? You have an input vector, and we are using f to briefly indicating the network function as a mapping function, and we can specify what's the output. If the network function have this particular parameters. We will change the input, right? We can have a different output vector. So given these parameters, we can define function, right? Given the network structure, we can define a function set, right? And the functions in this function set was determined by these weights and bias terms, okay? So this is if we want to make it more complicated, right? So, before in the previous simple example, like we have only, three layers, right? In addition to the input, but we can, keep stacking, more layers, right? In between the input and output, right? You can stack like 100, even 1,000 if you want, right? So you can, put as many layers as you want. So these are called the hidden layers, okay? And for each of the hidden layer, you have all these neurons, right? And they are, fully connected with the neurons in the previous layer. So you can see all these arrows, right? So they are connected with each other, okay? So then it's easy to understand, right? The deep learning means, how deep is your network, right? So the more layer you have for the network, we consider the deeper the network. Okay, so here I'll just give you a couple of examples, right? Some of the, a very classical neural network architecture. So this 2012, this is the AlexNet, right? So that's the first, deep neural network that wins the image classification challenge, right? Actually outperform significantly as compared to other competitors, which is our non-deep learning approach. So it has 8 layers, and we have later year, 2014, we have VGG 19 layers, and the Google have their GoogleNet, right? Has more layers. And in 2015, and the ResNet, right, which is probably the most popular network right now, has a lot of citations for this residual connect network, like I believe like maybe 60,000 citations already for their paper. So kind of the most popular network is being used still. People, when they have different variants, right? So for the ResNet here, they have the deeper network, goes beyond 100, right? Before it was only like 20 or 19 layers, but because their special structure called the residual connection, it makes them to able to scale or build a much deeper network beyond 100 layers. Okay. So obviously, I'm just giving you some of the classic examples or networks, right? So ResNet is 2015. Now we are 2023. So there's also other like follow-ups works, after residual, like the DenseNet. But there's no very drastic change after ResNet. So DenseNet is basically very close. You have more dense connections. But there's not much drastic changes, for the convolutional neural network after the ResNet. There's, some, modifications like the attention mechanism, other things, but we didn't, see there's a significant change or breakthrough in terms of the architecture. Although there's also, if you want to see, know how things going, forward in terms of the, how deep right now we can build. So right now we can build like thousands, layers if we want. And, we call this like a very large model or foundation model. They can be very deep. And, one field is called neural architecture search, right? So before all these, we can consider these are the engineered network, right? So we have some, experience, right? These are the hand engineered, right? Why do we come up with the skip connection, right? And so the neural architecture search is you basically like, give some building blocks, right? This is convolution, pooling, operation, batch norm. These are the like basic building blocks, right? Just like a Lego, right? So you have some basic building blocks. Then we can using some of the search algorithm to automatically construct a very deep neural network, right? So it's not hand engineered anymore. It's basically developed by using that building blocks and have a very large search space to combine or stack those components to automatically generated networks. But yeah, we'll maybe later talk about more details, from neural architecture search. But just to give you some idea, right? After the ResNet, there's not a lot of significant changes in terms of the CNN network. But neural architecture search may be one, domain that can come up with very different structure because these are the machine generated network architecture. Of course, we have these kind of vision transformer, right? And, become very popular in the recent years. But yeah, we'll talk about later. But here, just to give you a couple of examples, right? How, network evolve in terms how deep it can be. So and the next component, very important component, is the activation function, right? So there's we've talked about this sigmoid function, right? So this blue curve is the sigmoid function, right? Trying to squeeze the number, into the range of 0 and 1, and the red curve is the the partial the derivative or the gradient, right? Because in the back propagation we're gonna compute the gradient, right? And there's also other activation functions, right? Besides sigmoid, right? We have this hyperbolic tangent and this rectified linear unit or ReLU. So you must have probably heard of this ReLU in a lot of these classical neural networks, right? These are the common activation functions being used, right? So it's very simple, right? So the activation function GZ is max, 0 and z, right? So if the input is less than 0, then you output 0, okay? If it's greater than 0, then you output that input value, right? So if we plot, into a figure or curve, right? So you have this, before or smaller than 0, you basically have 0, right? If greater, then you have this kind of linear function, right? Okay. So one thing to note is that all these activation functions are nonlinear, right? So all these, based on the curve, you can see, right? So these are nonlinear functions. So the question is, why do we need a nonlinear activation function, right? So the purpose of this active function to be nonlinear is that, if we, just look at this example here, right? If we want to build a neural network, right, trying to correctly classify these simple two classes case, right? We have the red dot and the green dot, right, in the 2D space, right? If we only have the linear function, right, maybe this is, maybe a linear regression or logistic regression, right? So you have this linear function, right? You basically have a line to separate these two classes, right? So in this kind of, in this example, right, it's very difficult to kind of perfectly have a line to separate these two classes because, all these overlap between these two classes. Of course, you can still using some method, right? We can using the kernel trick, right? To, make into higher dimension, right? If we lifted this example, these points into the 3D space, right? Right now it's 2D, right? You cannot fit a line to perfectly separate these two classes, but maybe we can using some kernel trick, right? To lift these data points into higher dimension, like a 3D, right? Maybe you can have a linear function, right? Like a linear plane to separate these two classes. So it's possible, but if we don't do that, it's not going to have, perfectly separate these two classes based on the linear function. So we need some non-linearity in the, decision boundary, right? To kind of wiggle around, these, different samples, right? To have these perfect separation for these two classes, right? So we need to have this kind of non-linearity to approximate very complex function, not just a simple linear function, okay? In the neural network, right? So if we only using the linear activation function, right? So for all these layers, if we are using the linear activation function, no matter how many layers we stack, right? You can stack hundreds of thousands of layers. Essentially you can collapse into just one, right? And single layer and with linear function. So still there's not much, complexity you can introduce to this mapping function because everything is linear. You basically have collapse into one. Okay. And as I mentioned, right, for this kind of linear activation function, it has limited, capability, right? It's not have enough power or modeling complexity to model these kind of complicated input data. So here are the three, common activation function we've talked about. They all have some, can be considered as limitations. For example, the sigmoid function, right? If we look at the gradient, right, which is the red curve here, right? You can see the gradients are very small, right? All like less than maybe 0.4 here. So because we have multiple layers, right? When we do the backpropagation, compute the gradient, right, from the last to the initial layers, right? We using the chain rule, which we'll discuss the details later. So you basically multiply them together, right? So you multiply a small gradient and you multiply a small gradient, small value. Yeah, then you can see there's eventually you can have like a vanishing gradient, right? So this gradient will become accumulated gradient will, eventually towards zero. So this is not what we want. In that case, then you pretty much learn nothing for the network. So I mean, for the linear ReLU had the same problem, right? It's not like this solve this problem, right? If you look at ReLU here, if we compute the gradient, right, the derivative here, we have either 0 or 1, right? So again, here we are not totally emulating this kind of small gradient. We have a gradient equals to 1. So this vanishing gradient problem still exists. So to address this issue, right? So there's a couple of solutions we can use, and this there's a couple of kind of improved version or variants of ReLU, right? So this is called the rectified linear activation function. So basically, I mean, you can using some of the on the negative side, right? Instead of just 0, right? You can add in some of the slope on the negative side, right? So this is the generalization of ReLU, right? So not on the left side, less than 0, you can add a small slope, right? So we have this alpha, minimize z, and the 0. So this alpha is kind of learnable parameter, okay? So this is the generalized ReLU. Okay, so those are the activation, some of the common activation functions we can use in the neural networks. Now we can talk about the output layer, right? So this, you may also heard the softmax layer as the output layer, right? So in general, the output of the network can be any value, right? Because as we see before, right? So we have this input, or we have this weight, and we can using different activation functions, right? If we are using ReLU, right? So we have like max, 0, and a z, right? So if the z is a positive value, right? Essentially the output can be any value, right? From z to positive infinity. But as output, right? These kind of arbitrary value is not easy to interpret, right? Let's consider an example, right? If we want to do like digit classification, right? We have 10 digits from 0 to 9, right? But if you just output like a value like 100, and then you also have another neuron output a value of 200, another one maybe 0.5, right? How do we interpret this, right? How do we decide, right, which one, what kind of decision we can get, right? It's kind of hard to interpret these output. So an easy way, for this kind of classification problem is the probability, right? It's like the logistic regression, right? We have this probability, or if it's greater than 0.5, we have class of 1. If less than 0.5, then we can have a like class of 0 or -1. So if we are using probability as interpretation, right? So basically, we can specify the output should be a value, right, between 0 and 1, right? So that's the probability. And, because it's a probability, we have this property of, the sum of them should be equal to 1, right? So we consider all the scenario, and, we sum them should be equal to 1. So in this case, it's going to be much easier to interpret, right? So if we have a highest probability for one particular neuron as output, then we probably can consider that may be the class we want, right? So to achieve this, what do we do is we can have this softmax layer to achieve this. So it's very simple, right? So you have this, input z here, and we go to the exponential function, right? And we can do the sum them together, right? Basically, we need to normalize them so that when we do summarize the probability, it will equal to 1, right? And in this case, we'll just whatever the value you have and divide it by these normalization term here. So in this case, we are ensure we have an output has a value between 0, 1, and all these output will sum to 1. Okay, so we kind of have this kind of probability interpretation of the output. Okay. So let's look at an example here, right? So if we have this, input 3, 1, and a -3, right? We, do the exponential, we get these values, right? So we sum them up together. And also we're using this summation as the normalization term, and we can get a, output for this y1, y2, and y3, right? So these are the, we can consider these are the probability for each of these output. Okay, so now let's go to the second step, right? How can we, measure or evaluate the goodness of the function? So we, in the first step, we already know, right, how we can using neural network, right, the basic unit of neurons to build a neural network, specifically fully connect feed-forward neural network to specify a function, right? So in this case, the next step will, how we can using some of the training data and evaluate how good is that function. And later we can decide, right? The best function we use for testing or inference. Okay. To demonstrate that, let's using a specific example that is the handwritten digit recognition, right? So you recognize the digit from have 0, 1, 2 towards 9. Okay, you have these 10 digit. Okay, so basically you have these input digit image, right? So here is a input image, handwritten 2, and you go to the system or machine learning algorithm, right, to ask for what is the output of this input image. So we can to make a form, the machine can, easily process. We can take these input matrix. Let's, consider this is a grayscale. Okay, just a single channel, not color image, right? So basically just a 2D matrix. So 16 by 16, then we can, flatten these matrix, right, into a giant, a large vector, right, x1 to x256. And go through this machine on the mapping function, and then what is the output? So the output is going to be a 10-dimensional feature vector, right? Because we're doing 10-digit recognition, right? 0 to 9. Okay, so each of them maybe specify a particular digit class, right? This y1 may be corresponding to 1, and 2 corresponding to 2, and y10 corresponding to 0. Okay. So what we need is, a very good mapping function, right, to able to predict the input correctly. So as we say that, right, so if we do the vectorization, this is the input 256 dimension vector, right? Of course, this depending on the input resolution of the image, right? Here we are using a very low or small, resolution of image, 16 by 16. But if you are larger input, right, like 100 by 100, then the input dimension is going to be larger. Okay, and the output is going to be 10-dimensional vector. Okay, and the machine learning algorithm will build this neural network. Okay, yeah, so this is some detailed how you can do the vectorization, and this is the output. And right, and if we follow the previous building blocks of the neural network, right? So for the output, we're using softmax to have generate like a probability as a very good interpretation of the output, right? So this basically tells you like can be like measure of a confidence of a particular class, right? If you have a high probability, and then there's a high confidence, maybe this input image is going to corresponding to this particular class of digit 2. So in order to train this model, right, deep learning model, we have to prepare the training data, right? So we collect a bunch of training data, right, which is these digit images, and we also, annotate their corresponding label. So we consider this is the accurate and ground truth, right? So for each of the input, we have a corresponding label. And then we'll have the learning target defined on the training data. So given a set of parameters, right? Let's, using the, the feed-forward neural networks, right, as our, mapping function. And so in this case, if I give you, let's look at this particular example, right? So this is input digit of 1, right? So we have a ground truth. Because of training data, we know the ground truth. So this is the target, right? So if y1 is, corresponding to digit 1, right? So obviously we want to have a desired output of, y1 equals to 1, right? Have the highest confidence. Absolutely sure this is corresponding to y1, which is digit 1. And the other will be have the probability of 0. So this is like the ideal case, right? Very accurate. I'm gonna 100%, this is a digit 1. But in the, at least in the training process, right? So we are not going to see this kind of perfect close to the ground truth prediction, right? We are gonna make, this network is going to make some mistake, right? It's not going to generate this perfect prediction. But ultimately, the goal is that after we do some of the training and optimization, hopefully this network can predict output vector looks like this, right? Like a perfect, ground truth label, right? This, we call this one-hot encoding, okay, by the way. So here, the goal is that we want to make the prediction as close as possible, right? And then how do we measure that, right? So we have to define a loss, right? So here we basically want to specify a specific loss, right? So that we know that maybe in this, by specifying or compute this loss, we know how far we are, away from a very good model, right? Or close to the ground truth. So typically we can using, like a squared arrow, like a mean square arrow, right? So this is a prediction vector, and this is like the ground truth, one-hot encoding vector, right? We can measure the difference, right? We can using the mean square arrow. We can also using the cross entropy between the prediction and the, the target, right? These are the commonly used loss to specify, how good right now, is the model. So this is just one example, right? Remember, for our training data, we have a training set, right? We have multiple, training images, right? So this is for one particular image, digit 1. Maybe we have other images corresponding to other digits, right? So we'll, do this for all these training data, right? We have the input, another input will do this prediction, and we compare with this target or ground truth, right? We compute the difference or the loss, right? And we can accumulate the loss for all the examples in the training set, right? And in this case, the goal is that we want to minimize the sum of the loss, right? We want to minimize the total loss for the entire training set. If you make a small error for the entire training set, which means your model did a very good job in terms of prediction correctly, right? So the goal is to make the loss as small as possible. Okay, so let's, here, these are kind of illustration, right? We have all these, different training data we input into this neural network, generate the prediction and compare with the ground truth. And we can have, individual losses, right? Then we can summarize them together, right? If we're using this kind of, if we're using this squared loss, right? We can sum all the loss from all the samples, right? And we want to make it as small as possible. So in this case, we've trying to find a function in the function set that minimize the total loss, right? Remember, as I mentioned earlier, right? So this neural network, the parameter is kind of indicating like a function set, right? If you change the parameters, you have a different function. So essentially, we want to find a set of parameters that give you like the best, output, so that the loss is to the minimum. Okay. So once we find this network parameter, right, theta star here, then minimize the total loss, and we can, use it as the, the best function for the testing, right? So because this function like make the, total loss of the training data to the minimum, right? So we can use that for the testing. Okay, so this is very simple. The step 3. Once you have this best function, then you can directly use that for inference. Okay. Any questions so far before I move forward?